In this lecture, we are going to continue our discussion of Module 3 following our live lecture number 2. So please do watch lecture number 2 if you have not yet. And we will start with Module 3 in this video, looking at conservation of mass and how we can apply Reynolds transport theorem to the conservation of mass. So we remember that Reynolds transport theorem had a term B and a term beta that could be replaced by any property. So any property could replace this term B and beta. So for conservation of mass, what we're going to say is that B is equal to M and beta is equal to dm over dm. Okay, that's the definition of beta. Beta was just the property dB over dm, which turns to be dm over dm. So we can say that beta, in this case, for conservation of mass, would just be equal to 1. And so we can write the equation, the general equation for Reynolds transport, and we can write the most general form, which is a deformable case, where we have essentially our Reynolds transport theorem with m replacing our values for b and 1 replacing the value for beta. So if we write that out, we have that dm over dt of the system is equal to d dt times the integral of the control volume of 1 times rho dv. Okay, we just have 1 times rho dv because 1 is our replacement for beta. Okay, so that's our first step in the equation. And then we have the two terms that are crossing the control surface. So we have plus the integral of the control surface of rho. So 1 multiplied by rho times v in the n direction, dA out, minus the integral of control surface. I'm not going to write the 1, I'm just going to write rho times v in the n direction, dA in. So in case the velocity is not in the same direction as v, we have vn. Okay, and that would be dA in. Now, what we're going to do now is we're going to add a term under our v. We're going to add a term called vr. So we're going to call it vr. We're not going to call it v. And this is for the most general case. The reason we're going to call it vr is because we're going to say that vr in the most general case is equal to the velocity minus vs. And what this is essentially accounting for a problem where we would have a control volume that would be moving. So remember how we discussed a control volume that could be moving, for example, following a boat or following a car? Well, we now have this relative velocity term that is accounted for. So this is relative velocity. And this Vs here is a term defining the moving speed of the control volume. So if the moving speed of the control volume is 0, if the control volume is fixed, we can change that Vr to just V. Okay, and then it would just become our regular equation with just V. If we don't have a fixed control volume, we have to take V into account with the moving speed of the control volume. Okay, so this is our most general equation. And we'll do some examples where we have some moving control volumes so we can look at what happens when we have that, but we'll do that later on. So if we now have a fixed control volume, and we look at just a fixed control volume as opposed to a moving one and trying to simplify our problem a little bit, we can say that the dm over dt of the system is equal to the integral of control volume times d rho over dt times dv. So we're bringing the dt into the brackets because we're going to talk about the change in density times dv plus the sum of I, so however many outlets we have and however many inlets we have, we can simplify this to the simple form, which is rho I AI VI, which we've already done an example on, out minus the sum of I of rho I AI VI all in, and that would be our equation for fixed control volume. Now, looking at this, what can we say about when we have conservation of mass, looking at the first two equations we derived, what can we say about our conservation of mass? So we have this first equation here and a second equation here. What does conservation of mass mean? Conservation of mass means that mass in the system does not change. Therefore, dm dt of the system for a conservation of mass problem, when the mass is conserved, is always going to be equal to 0. So we can add that this is equal to 0 on this side and that this is equal to 0 as well. So we can add an equal to 0 in both of these equations. So that helps us understand what's going on. Now, if the flow is steady, is said to be steady, and mass is conserved, so remember, steady flow means that the mass inside the system is always the same, okay? Or the property inside the system is always the same. And therefore, we can say that if we have flow is steady and the mass is being conserved, we can say that the first term, which is d rho dt in our equation, would be equal to 0. So the first term in our equation would disappear. So we would be left with 0 is equal to the sum of rho AV out minus the sum of rho AV in. Okay, and if we rearrange this, it means that the sum of rho AV in is equal to the sum of rho AV out. Okay, it makes sense. Essentially, it means that the sum of the mass flow rates in has to equal the sum of the mass flow rates out. And this can be shown in an example of a steady flow, again, through a pipe. So if we have a flow through a pipe, we have a control volume within that flow, what we're saying is that at point 1 and point 2, we have some mass coming in and some mass coming out. And we can say that this mass flow rate coming in would be equal to the mass flow rate coming out. Okay? On a different scale, what if we looked at a system where we had, on a different idea, what happens if we have, for example, a bathtub filling up? So let's say we have a bathtub and we have a faucet with a bathtub filling up. Okay? And this is water. If we have a problem where we have the bathtub filling up, we now have a change in mass with time. So the problem becomes more complicated, and we have to take into account the first term, which has the integral of CV d rho dt times dv. We have to take into account this term in this case if we have a transient filling of a water tank and our mass is changing in our system. Okay, but for now we're going to focus on flow systems, and the flow can be said to be the sum of mass flow rate in is equal to the sum of mass flow rate out. Now, if we have, so if we go even further with this and say that in, for example, our pipe flow, if a fluid is incompressible, we can say that density is constant. Okay, so the density could be constant between 0.1 and 0.2, for example, in our pipe flow. Or the density might not be constant, in which case we have to use it. But if the density is constant, we can simplify our above equation of the sum of rho AV in is equal to the sum of rho AV out. We can simplify by canceling the rho terms since they're equal. We know that the two terms are equal. And we're left with the sum of AV in is equal to the sum of AV out. And if you remember correctly, Q, which is our volume flow rate, is equal to velocity I times AI. This is our volume flow. It's in meters cubed per second. So we can rewrite this as the sum of the volume flow in is equal to the sum of the volume flow out. This is only the case when density is constant within our flow. Now, this is obviously assuming a simple case. So this was assuming simple case, which is we had assumed that the simple case was a 1D flow. If the flow is not one-dimensional, so if the flow is not one-dimensional, we have to integrate on the surface for our velocity and our flow rate, essentially. We have to integrate on the surface. But it's not that complicated. Okay, so we have to integrate on surface. And if the surface is pretty simple and we know our velocity profile, it shouldn't be too hard. So a one-dimensional flow, just so we keep our logic together, if we have the inlet here, a one-dimensional flow would look something like this. We would have a flow with all the arrows within the flow at the same velocity. Okay, this is called a 1D flow. A non-1D flow, which is a more realistic flow, would look something like this, that we already talked about, would look something like this, with arrows changing in velocity where the velocity in the middle would be higher than on the sides because of the wall resistance. Now, in order to figure out the normal component of velocity, and this 1D flow could also look something like this, okay? So when you have turbulent flow, you could also have a flow like this with like different shapes based on completely random flow, in which case we would have to integrate our flow as well. So we can say that in this case, m dot along the control surface or along this inlet would be equal to the integral of rho times v dot n, okay, or v sub n, same thing, times dA, and QCS, our Q along the surface, would be integral of, without rho, just Vn times dA. Okay, maybe our velocity is not always straight at 90 degrees, so we have to take into account that we're looking at only the normal component of velocity. Now, we can get the correct volume flow so we can get the correct integral if we do a little trick. We can use the average velocity, and if we use the average velocity, we'll get the same volume flow. So we can find it by using velocity average. And we know that V average, if the V average is equal to Q over A. Okay, if we rearrange the equation that Q is equal to V average times A, we can rearrange it to write that V is equal to Q over A. And we wrote right above that Q is equal to the integral of V dot n dA. So we can say that V average is equal to 1 over A times the integral of velocity in the normal direction times dA. So we can find V average that way. So we can just average velocity by finding the velocity throughout the area and the velocity profile throughout the area. So if we can draw the profile, we can then do an integral of that profile and find the average velocity. In the same way, we can find the average density if it does change. So if the density does change, we can find the density average by doing 1 over A times density along the surface dA. Okay, so we just look at the sum of all the densities throughout dA, so density at one point, density at another point along the profile, and then just divide by A to get the average. And by using the average, we can then just say that m dot cs, for example, would be equal to rho times A times V average for non-1D problems. Okay, so just a little bit of a more complicated thing, but definitely manageable. So the next thing I want to do, now that we've gone over the theory and we sort of understood what's happening, is to look at an example problem and look at a pretty complex example problem where we have some changes in water height and water amount within a control system, within a control volume. So I'm going to copy over the problem now. And we'll get started with the example. Okay, so in this example, we are told that the tank in figure 3.5 is being filled with water by two one-dimensional inlets. So we know one of the first things we can say is that we know we have an assumption that we have 1D inlets, which makes it very easy. The velocity in is just velocity for the whole profile, so it makes it very simple to understand. Now it says that air is trapped at the top of the tank and the water height is h. Okay, so we have a certain amount of air that is trapped at the top of the tank. So we can see the air here that is trapped. And we're told to find an expression for the change in water height dH over dt. So we have to find an expression for the change in water height dH dt. So this is actually a pretty complex problem because we've never really done this before. But the idea here is make some assumptions, and then we're going to write our equation for control mass, and hopefully for conservation of mass, and hopefully we'll be able to come out with something for the expression of dH/dt. So as we can see, 1 and 2 are coming into the system. So if we look at, we have inlet 1 and 2 coming into the system, we have nothing coming out of the system. So we know that if there's more water coming in, we know that this level of water has to go up. There's no other way. This water level has to go up because there's no exit. Okay, so we only have flow in. So we're going to start with our original equation for conservation of mass. So some of the assumptions we can do before we get started is that so we have 1D inlets, and for now that's pretty much the only assumption we can make. So let's start back with our original equation. So start the problem, start with original equation. And from the original equation, we'll be able to solve the problem. So we're not going to start with the most complex equation with a moving system. We know that we have a fixed control volume. We're not told anything about our control volume changing, so we can add to our assumptions that we have a fixed control volume. Okay, so our assumptions are 1D inlets and fixed control volume. So we start with the original equation. The original equation said that d dt of the integral of control volume rho dV plus the sum of rho AV out minus the sum of rho AV in. And we know that this is equal to 0 because dm dt of the system does not change. Okay, so the first thing we can say is that the flow out is going to be equal to 0. So the first thing we can say is that the flow out is equal to 0. So what we can do is we know we have no terms with flow going out. So we can say that our flow out is equal to 0. We can also say that the mass in our system in this term, so we can say that in this term, the mass in the system, does it increase or decrease? The mass of the system increases with time. Okay, and we know it increases with time because we have some flow in. Okay, if we have some flow in, that means that that's going to be the rate at which it increases with time. So if we rewrite this equation, we can now write that we have d dt times the integral of control volume rho dV, and we're going to bring this term right here, we're going to bring over to the right side. So we're going to make them equal to the positive of rho AV in. And we know that rho AV in, it comes from inlet 1 and inlet 2. So we have rho 1 A1 V1 plus rho 2 A2 V2. Okay, so we're left with an equation that says that the increase in mass with time is equal to the added mass flow rate with 1 plus the added mass flow rate of inlet 2. Okay, it makes sense. So we can break down, so now in order to get, so now we have an expression for our mass coming into our system, okay? And in the question, it asks us in question A to find an expression for dH dt. Okay, so it tells us to find an expression for dH dt. So we know that dH dt is going to increase due to the fact that the flow is going up. So what we're going to have to do here is we're going to have to break down the term on the left side. So we're going to have to break down this term right here. We're going to have to break it down, and we're going to have to try and understand what's happening within this term, okay? And we're going to break it into pieces, okay? Because there are multiple pieces within our control volume. So as you can see, our control surface circles the whole system. So we have to take into account the density of water, and we have to take into account the density of air. Okay, so we're going to write that this term here is equal to d dt from, and we're going to change it in terms of cross-sectional area. So we're going to say from 0 to h, okay, from 0 to little h, we have density of water, okay, so density sub W, times the cross-sectional area A times dH. Okay, so this is cross-sectional area A. And dH is the change in height, okay, the change in little h. And so we have that this term right here is essentially equal to dV. So we have dV is equal to A dH. And we're going from 0 to h. So we've changed our expression from volume to in terms of height because we have a constant cross-sectional area. Our cross-sectional area is constant, therefore we can break it down into area times distance. Okay, the only thing changing is the distance, not the cross-sectional area. Okay, and then we have a second term that we can also break down in terms of height, which is going to be, so I'm going to close this bracket here, which is going to be d dt of the integral from little h to big H, which has the air. So it's density of air times A times dH, okay, the change in height. And we have that this is equal to we have that this is equal to just the right side of the equation. So we have that it's equal to rho 1 A1 V1 plus rho 2 V2, sorry, rho 2 A2 times V2. Okay, so we can keep writing this equation and now solve for our integral. So we can now solve for what our integral is. So we can do the integral and then we'll do the differential. So we're going to solve both integrals. So we're going to solve this integral here and we're going to solve this integral here and rewrite the equation. So we have that this is equal to d dt times rho w. Okay, we assume there's no change in density in rho, so we can take it out, times area. Area also doesn't change, so we just have the integral of a dh from 0 to h. So we're just going to have h minus 0. Okay, so that's our first integral solved, assuming that density is constant and area is constant. We're not given any information on the change in density, therefore we're just assuming that density is constant. And the second term is going to be d dt times rho of air times a. Okay, again, we're taking them out because we're assuming they're constant, of h minus h. And we know that in this term, we can say that the air is trapped. So what happens when air is trapped? When air is trapped, the differential of rho times A times the change in H, what does this term go to when we increase the height? This term slowly goes to 0. So what we can say in this problem is we can assume that over time, this term is going to go to 0. Okay, so we're only going to look at the left term, and I'll write exactly why. So the left term, if we now do the differential of the system, we can say that rho w times a times dh dt, okay, plus something that goes to 0. So why does this term go to 0? Let's write it out completely. So we can say that the term with rho air, so the term with density air, goes to 0 or vanishes because the differential of something, or because the rate of change, okay, the differential is rate of change of air mass, the rate of change of air mass with time is 0. Okay, so the rate of change of air mass is 0. So we're compressing the air more and more and more, but we're essentially have a system that has no change in mass. And since it has no change in mass, the differential of that change in mass is actually equal to 0. So what we can say is that d dt of the mass of air is equal to 0. And that's why this term goes to 0. Okay, just wanted to make sure that it made sense as to why this term goes to 0. Okay, so moving forward from this, we have now simplified our equation a lot. We don't worry about the air anymore because there's no air added to the system or taken out of the system. So this term just goes to 0. There's always the same amount of air. Okay, so we go to that, and we can now say that we can now rewrite our equation as rho w times a dh over dt is equal to rho 1 a1 v1 plus rho 2 a2 v2. Okay, the change in height is only affected by our addition of fluid, and the change in height of the air is just a resultant of that, but it doesn't really matter to our equation. So if we rearrange this equation and say, well, we now can bring these two terms to the right-hand side, we can say that dH dt, which is our expression that we were looking for, dH dt is equal to rho 1 times a1 V1 plus rho 2 A2 V2 divided by rho water times area. And remember, this is not the area of the entrance, this is the cross-sectional area. Okay, so this is the cross-sectional area of our tank. Okay, so we can simplify this equation by saying, let's actually get rid of rho water, rho 1, and rho 2. We're not given any specific information on density, but we're just going to assume that all densities are the same for the water. The density at entrance 1 and the density at entrance 2 are just water. So we're adding water to our system. So we can cancel out the density. And so we're left with an equation. So we're just saying that rho W is equal to rho 1 is equal to rho 2. Okay, that's our simplification here. So we can say that dH dt with time is equal to A1 V1 plus A2 V2 over the cross-sectional area. Or we can write it as Q1 plus Q2 over A. So the change in height is related to the change in Q, the added volume flow rate over the area. Very simple. Very simple, but sort of a complicated way to get to the answer. But once we have that simplification and we understand that there's no more air being added, we can get rid of the air term, and we just have to rewrite the volume term in terms of height times area. So the two big assumptions we made in part A, just to go over them again, is this assumption right here, and I'm going to highlight them in blue. This assumption right here, that volume is equal to area, which is cross-sectional area times dH. And the second assumption we made is that this term goes to 0. And we explained why it goes to 0 because of this statement right here. Because we have no more air added to the system. Okay. And so it turns out that dH/dt is related just to the volume flow rate coming in over the area. Okay. So part B of the question, just to go back to part B, asks to compute dH/dt. So it tells us to compute dH/dt if D1 is equal to 1 inch, D2 is equal to 3 inches, V1 is equal to 3 feet per second, and V2 is equal to 2 feet per second, and the area T is equal to 2 feet squared. So the area T is our cross-sectional area that we're looking for. Okay, and D1 and D2 are the diameters. So this is diameter and diameter. These are the diameters of the holes. So diameter of 1 and 2. And this AT here is cross-sectional area. And it gives it to us in the diagram, right? We have in the diagram, we have a tank area T. So we know that the tank area plus the height is the volume, multiplied by the height is the volume. Okay, so going back to our equation, we can now say that we can essentially find Q1 and Q2. So that's going to be our first step, finding Q1 and Q2. So if we find Q1 and Q2, we already know A. So Q1 would be equal to pi over 4 multiplied by 3. Okay, so So it's multiplied by, so it's pi over 4 multiplied by 1 squared multiplied by 3. Okay, 3 is the velocity. So this is velocity 1. Now, here I have the velocity in feet per second. And here I have our measurement in inches. So what do I have to do to this measurement to rearrange it? I need to use the same units. So I need to use feet. So what I have to do is I have to change these units to something else. So I'm going to rewrite this as pi over 4 times 1/12, because 1 inch is 1/12 of a foot. So now that we have our units in feet, and then our velocity can stay in feet per second. And so we're left with a Q value, which is 0.016 feet cube per second, or cubic feet per second. Okay, this is really important. The units are really important, so you have to keep track of them. Q2, in the same way, is just equal to pi over 4 multiplied by 3/12, because we have 3 inches now, squared, multiplied by 2 feet per second. So we have a velocity of 2 feet per second. And so that term is equal to 0.098 cubic feet per second. Okay, so you have to be really careful with your units. And now we can just plug in our values into our equation. So we have dH dt is equal to 0.016 plus 0.098 divided by 2. And so we get that our final answer is 0.057 feet per second. So the height is changing of the water per second is changing by 0.057. So in engineering, the CV mass relation is used all the time. So in engineering, the CV mass relation is used all the time. And the reason it's used all the time is we always want to check that mass is conserved. We always want to check conservation of mass. But we always check it in a much faster way. So we just say we have a time term. So we know our first term is a time term that is only activated if we have something filling up or something emptying. So something changes within the system, just like we had in our previous example problem. And the other terms are the out terms minus the in terms, and we know that this is always equal to 0. So a change is only apparent if we have more in than out, for example, or more out than in. If in is equal to out, the time term just goes to 0. Okay, that's the conclusion from this chapter, essentially. So you can always use this relation that says, if we go back to here, we can always use the relation that says, so going back to the start, we can always say that dm dt of the system is equal to 0, and we can always use the right side of the equation being equal to 0. Okay? So that concludes our part 1 of the video lectures. So video 1 is concluded, and we'll go on to video 2 to look at the linear momentum equation and how we can apply our term B to linear momentum using Reynolds transport theorem.